CMC Systems webinar series. Thanks for joining. Today's webinar, Noise Figure Measurements with the PNA-X, is co-hosted with a team from Keysight Technologies. Just a reminder, your phone lines have been muted to eliminate any noise. At the end of the webinar, we'll open up the lines for any questions. And meanwhile, if you have any issues, technical or related to the webinar, please do send any questions through the chat box. So today's webinar is one-hour presentation by Maury, Keysight Technologies. He used the noise figure measurements. Noise figure is a critical figure of merit when designing components found in modern communication systems. You'll start with explaining the noise figure fundamentals and describe the common noise figure measurement technique used, and continue by introducing the cold source technique implemented in the PNA-X system. We will then describe the vector and scalar noise figure measurements techniques used to measure amplifiers and receivers. These noise figure measurements can also be applied to connectorized and on-wafer devices, and we will show how the PNA-X noise figure solutions improve the measurement uncertainty. As a topic, we will explain some of the extensibility of the PNA-X noise figure solutions to measuring noise parameters. In CMC test pool equipment, we the Agilent N242A PNA-X analyzer to measure up to 26.5 gigahertz, and also scale of measurements described today. Introduction to our presenter, Maury. He's an RF and microwave applications engineer with the Electronic Measurements Group at Keysight Technologies. He's working in various roles in high-frequency antenna and system designs and tests for over 25 years. For 17 years, he has been with HP, Agilent, Keysight, supporting our customers in Southern Ontario and across Canada in the aspects of test and measurement, from data acquisition solutions to ultra-high frequency VA and spectrum analysis. He has worked closely with the RF and microwave communication industry, both manufacturing and R&D. Critical part of his job, he delivers technology and instrument training on RF, microwave, and radio test solutions. Without a delay, I'll hand over the presentation to our speaker, Maury.
Thank you. Well, good morning and afternoon, everyone. As mentioned, I'll be presenting today on the technique that we have in the PNA-X form on noise figure in these complex measurements on your devices. So with the advent of the PNA-X,
Jean-Marc?
Yes, go ahead.
Sorry to interrupt. You just need to, we can't see your screen.
All right.
Thank you.
Moving forward, with PNA-X platform, we really designed it so that it can make what's called single connection multiple measurements. In the past, being able to make all of these types of measurements, like parameters, pulse movements, gain compression, AM to PM conversion, harmonics types of measurements, in the noise figure required multiple different setups, multiple different type of instrumentation, and so on. So now with the PNA, with the connection multiple measurements, everything's integrated in one instrument where you can actually connect your device once and make all of these measurements simultaneously. Today's agenda is going to be an overview of this figure. We'll talk about the measurement techniques that exist today. We'll also approach the PNA-X unique way of making noise figure measurements. And we will also talk about accuracy and limitations that exist in noise figure, not only in this technique, but in all noise figure techniques, and also how we can use this platform with external tools to extend that to making full noise parameters. So why do we care about noise figure? Well, Noise causes system impairment, so it degrades voice and quality of signal transmission. It limits the radar systems. It increases error rates in digital systems, changing and increasing ISI, intersymbol interference in digital systems, and so on. So it's basically a direct effect to signal to noise. Always increase that signal to noise by increasing the transmit power. Effectively, if you had a satellite system, it would be very difficult to go into space and increase the gain of those amplifiers, as it does take more weight and space and so on. We increase the path loss, but in most cases, our wireless systems require a point-to-point, which is communication, which is over very long distances. But it's really easier, less expensive to decrease the receiver noise contribution. Finish of noise figure. Well, the figure is the noise factor, I should say, is the signal to noise at the input over the signal to noise at the output, or effectively the noise at the effective noise at the output over the gain times the noise at the input. And the variant that we use today is called noise figure, which is basically the analog of the noise factor. Also reported in effective noise temperature. And if noise temperature is basically just a relationship of noise figure to degrees Kelvin. When we take a look at the available noise power of a passive termination, we call the noise power coming out of that 50 ohm termination what we call KTB. So KTB is Boltzmann's constant and bandwidth. So we usually say KTB, we usually mean 174 dBm in a 1 hertz bandwidth. So that is the total power coming out of that termination at room temperature in a 1 hertz bandwidth. Room temperature in our case is usually reported as 290 degrees Kelvin, about 17 degrees Celsius, which is a bit cooler than actual room temperature, but that's where we express KTB. So when we take a look and we convert dB of excess noise ratio or dB of noise to Kelvin, for example, a 15 dB of noise figure would be about 8,800 degrees Kelvin. Okay. So the chart basically of noise figure versus noise figure on the y-axis versus temperature in Kelvin. You take a look at the 3 dB noise figure point, that's about 288 degrees Kelvin. Okay, it's a little bit warmer than, cool, should say, than room temperature. And you see that it's not a linear relationship. As we get closer to 0 dB of noise figure, we see that the temperature drops very, very quickly, so the effective temperature. Noise figure and effect temperature are interchangeably used to report the noise figure of noise figure of an amplifier. Why is noise figure important in research and development? Well, when we are doing simulation and so on, we have an effective way of correlating noise generated by the system versus the actual noise of the amplifiers and so on, generated by the amplifiers and so on, compared to the system noise. It's the only way to optimize our transmit and receive systems is to understand the effective noise figure of the addition of the amplifiers and receivers and so on. So that improved accuracy in designing circuitry and so on. Very importantly, noise figure is a difficult thing to simulate. We can always add some amount of noise power, et cetera, as we go along. But especially for determining guard bands, how much specification are the specifications going to be for that receiver, for that transmitter, et cetera, in terms of noise figure. It's important in manufacturing. Also, the improved measurement accuracy results mean the smaller guard bands, so we can actually develop products and spec them tighter than their competition. In other words, the noise figure has been deemed, the money spec. So the lower the noise figure by a measurement of a device, the more you can ask for in the market for that device. So we have Keysight, Agilent, and previous to that, AP have been in noise figure measurement business for a very long time. So we have a very long legacy in that. And some of these products, especially on the bottom of this, you're probably familiar with noise figure and the noise figure analyzer, the PSA, or PXA platform. So today I want to focus in on the PNA-X noise figure techniques. So what exists out there today? Well, there are really two techniques that are very popular. One is the Y-factor method that's used extensively with receivers as a technique with a receiver, and the other method is a cold source or direct noise. A couple of others that are not very popular in multi-tone types of measurements, but these are the two that really are focused in the test and measurement industry. So the Y-factor method requires a noise source that has an effective ratio, or an excess noise ratio, I should say, with two states. So we make measurements using hot and cold states, and this technique of the Y-factor is extensively used in receiver architectures like the noise figure analyzer and spectrum analyzer-based solutions. Cold source technique used by the vector network analyzers, and we'll talk about why we prefer using that technique for Y-factor. It uses the cold or room temperature termination only, does not need states like in the Y-factor. And it's for a single connection as parameters and noise figure all at the same time. Take a look at the Y-factor technique. We see that when we need to connect basically a noise with an effective temperature off or cold and a temperature on or hot device, and at the output of the device, we would then use a noise receiver and make two measurements, P out at hot and a P out at cold. And if you take a look at the formula, we could see our famous KTB formula there. Gain is basically the gain, and in our case here it is unknown, and the temperature or the temperature of the excess temperature generated by the diviner test is also unknown. So both those, gain and the temperature of the device, have to be calculated from the measured results. One of the issues that occurs here is that the receiver itself also has a noise figure associated to it. It has losses and gains and so on in it. So we need to be able to calibrate that out. And the way we do that is to use that same noise source and connect directly to the noise receiver and do our calibration. So if you take a look at the bottom left, you'll see that the gain of the noise figure of the DUT is going to be equal to the noise figure of the system after calibration. This is the gain calculation and the receiver noise figure. So representation of the Y-factor technique. You can see we do on the left at the bottom, we do a P in cold and P out cold measurement. We then do a P in hot and a P out hot measurement up the curve, creating our gain curve. And the delta P out over delta P in is equal to our amplifier gain. Now, forget that these measurements are all being done measuring noise. Okay, so these are all power measurements that we're making. So some of the assumptions that we have for Y-factor technique is that the source, noise source, and DUT have a very good match and very well matched, so there's very little interaction there. Also, the source hot and the source cold have the same input match, so that impedance doesn't change. We also are assuming that the receiver impedance or match is effectively the same over frequency and an over power. And that the gain, when we calculate the gain from the powers, hot and cold powers, this is only if in case of S1 and S2 measurements. So a little bit of issue there in terms of gain calculation, but we could still effectively get a really accurate measurement in this case. So we take a look at noise figure measurements with Y factor. We get really good accuracy when we're making individual device measurements directly to the input of the receiver and directly connected to the noise source. However, we can have some issues in terms of making on-wafer measurements, animated straight ATE types of measurements, and for multiple ATE types of measurements. And the reason is that the source is now extended away from the device under test. Losses and mismatches that affect the overall accuracy and the assumption that the impedances are good never decay. So we're very careful when doing these types of measurements. Let's talk about the cold source technique. So the cold source technique is effectively we don't have a noise source, but we'll use a termination. Basically, the test port of the network analyzer is a termination. And since you'll see we have the same formula out here. The P out is equal to the KTB, the gain and the effective noise power. But gain in the analyzer can be measured very accurately using small signals. So we're able to calculate, or I should say measure the gain very accurately in this case, and then measure the effective noise power coming out of the device using a receiver, the network analyzer, and calculate what the noise figure is going to be for that device. The advantages, obviously, we have here is that there are mentor-corrected techniques available to us, network analyzer, that can help us increase the accuracy. This is a graphical representation of our cold technique. The slope is actually measured using an amplifier gain, so 2-1 measurement. Effectively give it a P in and P cold measure, and we can measure the overall noise power and calculate the noise figure. Compare both the Y factor technique and the VA or PNA-X technique for cold source noise figure. They have still their place. One does not replace the other. The Y factor technique is excellent in terms of making low noise figure measurements. We're directly connected to DT. Process, calibration, and in most cases, very accurate measurements when your device has a very good impedance match. The minimum uncertainty, unfortunately, goes a little bit far out when you start working farther from the device and so on. For the PX, with its more advanced error correction method, we can provide excellent accuracy in all cases of measuring these devices. It's especially true for in-fixture and on-wafer, because we can calibrate all the way out to the device under test. Let's talk about the unique PNA-X style. So there are two options. One's called option 28, and the other one's called option 29. Option 28 has an integrated receiver, and we'll see that in a second. And option 28 uses its own VA receivers. Okay, and you'll see by the slide up here that circle showing that we still have two techniques. One's called a vector technique, and the other one's called a scalar technique. So in both cases, vector and scalar could be used both for the internal noise receiver or the measurement receiver technique. And this is ECal that's on that test port, allowing us to do some source pulling so we can make very accurate device noise figure measurements. So it's a source tuner. technique is usually up to 2 times faster than the figure analyzer technique in many cases. However, because of the PNA and network analyzer capability of making many measurements in a very small span of time, customers are seeing a lot more details because we can actually do some very narrow frequency spacing in the sweeps. So the unique vector technique that we use here is to introduce the ECal, which is basically a multi-line calibration unit, which exposes different impedances to the device. We're actually able to make all of these measurements, all of these actually doing a source pull on the device. So the reported noise figure, a vector measurement, is the reported 50 ohm. It's not the impedance of the unknown system. Okay, so very important here is to say that not only are we going to be able to get a much better accurate noise figure because we're removing mismatch, we're also going to report to you the 50 ohm impedance. 50 ohm noise figure. So if we take a look at the network analyzer, behind test port number 2 is where we introduce the noise receivers. So they're dedicated broadband noise receivers, and they are not used for S parameters, but they're all used for noise figure measurement. On the left-hand side of the diagram, the external ECal required for vector-corrected noise figure. The thing for our higher frequency boxes are 45, 43, and 50 gigahertz, and also 67 gigahertz. We have the internal noise receivers. However, they only go to 50 gigahertz. And you'll see on the bottom left there that we integrated the tuner inside the box. Now you don't need an external tuner, but the internal tuner is available there to do all of the source pulling necessary to do the accurate noise figure measurements. And those built-in tuners are selectable calibration and measurement process. So if you think about it, we're making a lot of measurements, but effectively when we're making noise figure measurements with all those different source impedances that we're testing over, and the gain sweeps and the noise figure sweeps, we make 6 measurements in order to get an accurate noise figure measurement. So effectively, the met speed is very, very quick. Here, the PNA-X versus the Y-factor method, we could see that a network analyzer, you'll see that we have almost 10 times speed improvement when we're looking at 201 points of measurements versus the NFA spectrum EXA. So that's the complete spectrum analyzer line there. Okay. Improvement, not one of the most important things for research and development, but definitely for manufacturing. So when we look at, I said we were talking about vector, and we also have a scalar noise figure technique. A scalar noise figure technique does not use that pull technique. It basically uses the inherent impedance of the system as the source match. Okay. So it still uses the same cold source methods. We just don't do the vector portion of it. Okay. So the advantages are the setup is a bit simpler. The cost of the system is a little bit lower because you don't need that extra ECal. And the other technique more closely represents a noise figure measurement using by the Y-factor method. Okay. Because the factor method does not report the noise figure at 50 ohm impedance, but at the impedance of the system. Okay. So a scalar portion of the PNA, it's more representative to system noise figure and could be related a little bit closer to the Y-factor method using the spectrum analyzers. Compare the vector versus scalar noise figure calibration, you can see that if you just look at the gain curve, like the light blue curve that goes up there, that's the gain. You can see in both cases they're going to be really close. However, when we compare the noise figure measurement, and that is the brown line, orange, green, and purple line there, and we've moved the reference level away from each other, so they're effectively all reporting about 3 dB, 3.5 dB noise figure at the marker. So we basically moved those other two reference lines down to see them individually. So the brown line is the vector, and you can see that there's very little ripple across there. So we've effectively removed a lot of the mismatch error and reported you the 50 ohm noise figure. Also, you can see the orange line is where we added 6 dB of attenuation to the internal port, and we see that effectively it has close to the vector. But as we move away from that attenuation, which would change the port match, we can see if a 3 dB port match or a 0 dB attenuator setting, now that's basically the port is looking right at the sources inside, you can see that there's a lot of ripple that occurs. So that ripple is basically due to mismatch between device and the source. Compare both the PNA-X and the figure analyzer, because noise analyzers have been around for a long time. We can also, by overlaying them here, see the two techniques using the same device. We see that the gain of the device on the NFA seems has a lot more ripple. The PNA-X gain seems to be a lot more, a nice reason curve. And take a look at that orange line that's overlaid over the brown vector corrected measurement. You can see that there is a lot of ripple there too. So most of that ripple in factor method is due to mismatch between the source and the device and receiver. In the PNA version, we remove all of those, effectively give you a much smoother representative of the device under test. So take a look at the speed improvements, the vector versus scalar. You can see that the scalar does have a faster measurement because we don't need to do that source pulling. So here's an example of the block diagram of your 26.5 gig PNA, where we would introduce the ECal on the left-hand side at the bottom. And on the right-hand side, you'll see we would switch to the noise receiver to make the noise measurements. So the device is pre-matched and you're connectorized, data setup, no external measurements, other external. This is necessary to make this measurement. If we're deciding on doing scalar noise, then just remove and not connect a tuner, and it stays the same. For example, this is the higher frequency network analyzer. The noise receivers are still again on test port. In a 4-port configuration, the noise receivers again are only found on port 2. And let's skip that. People are asking also about, hey, what about noise power parameters? There are a whole bunch of different noise power parameters available in the analyzer. We can measure display to the available power, the incident power to the device, all related to 50 ohm. We can express it in absolute terms or in relative terms, and also give you the system parameters. So the effective noise power, at the input, at the output, and all of your S parameters, all available all at the same time. Okay. It's an example of where we can actually tell it, well, we want to see the DUT relative noise power or the DUT noise power density. So all of these measurements are available to you so that you can actually effectively take a look at what the total noise power going in and the total noise power coming out of your device and see if the system is operating correctly and if your measurements are actively correct. The noise setup is actually very, very simple. So for those of you that are familiar with the PNA-X and its different measurement classes, a comes up like this for the setup. So everything can be done in one dialog where you get up the start and stop frequencies, the number of points, power levels to deliver to the device when you're doing S parameters. And also on the Noise Figure tab, we then have access to selecting bandwidth you want to report the noise figure in, the ambient temperature in your lab. You can actually change that, and you'll see that the noise figure value will change slightly depending on what the temperature of the ambient is. And also the impedance states. So you can tell how many impedance states you want to for the vector case. So calibration, if those of you that are familiar with the network analyzer, the PNA, calibration is really not that much more complicated than the vector cal. So the vector calibration is either done using an ECal, or a vector, or a mechanical cal kit. And the noise figure portion is calibrated using either a noise source, a power sensor. And those techniques are available to you. You can select which one you want. We'll talk a little bit more about the accuracy differences between the two. So wafer calibrations. So two fundamental approaches using a using the cal wizard to do a cal all channels, and then calibrating at the coax interface, and then de-embedding the probes. So what's about the noise figure technique that all of the embedding that was available in S parameters are all available also. You can extend your noise figure plane all the way out to your device, either on wafer or through fixtures and so on. So look at how we would do that. We calculate on wafer noise source or power meter, depending on which technique you want to use. If you have, and you do a full 1-port cal at that interface as the noise source, and you would do your TRL on wafer and extend the noise cal out to the probe tip. So very full technique. So here's another example where we would actually, which is slightly better, which is actually doing the noise power cal right at the test port and then doing a vector cal and extending the noise reference plane out to the device under test. As I mentioned before, because of the fact that we have fixtures available in the network analyzer, we can characterize those adapters from our plane for our noise figure all the way to our cal plane to our device, and be able to de-embed those straight out of the measurements. So the technique is available to do accurate measurements, obviously. So one of the important things, just like the Y factor method, is we need to characterize the receiver. So in the network analyzer, we have to do the same thing. So we characterize the receiver to find out what its bandwidth is, what its noise power is, what its is, and so on. And that can be measured either using a noise source or the power meter technique, where power meter would be used to calibrate the transmit out of the network analyzer, and then we connect the transmit side, so we're pointing to port 2, let's say, the network would then use that source to find out the gain and the product or the bandwidth product of the receiver is. So then the calibration is done in that technique. So a meter-based receiver characterization would look like this, where we'd sweep the receiver and you would the dual sideband of the receiver itself, since we're dying type of receiver. And calculate what the equivalent receiver noise bandwidth is from those measurements. So figure user interface looks a bit like this, where we can actually select what calibration method, vector, or S parameter only, we would then select the tuner type. Is it internal or external? Then the receiver characterization. Are we going to use a noise source or use a power meter? So for the all, we'll see the power meter and noise source in that display to the right there. Okay. So one of the important things to note too is that when using the network analyzer noise option and you want to select in 24 megahertz bandwidths, a noise is required to calibrate the receiver for those. But for anything narrower than 8 megahertz of bandwidth, the power meter works very well. So, is, well, how does that compare? How do both of those techniques compare? Well, you take a look here, and in the plot we have a like 0.5 dB division scale there, where we're overlaying both the rear cals with the power meter and the noise figure, and see that they're well within, like, if less than 0.1 dB of difference between the two, across each other here and there. So there's no real winner in this case. You have a noise source, that is a technique of doing it. If you have a power sensor, that is another great technique. Okay. What is option 28? Well, we've got option 29 as being the internal noise receivers. Option 28 is figure using the measurement receivers. So the same receivers we would use for S parameters. It works on all PNA models, PNA, PNA-X models. It will sometimes require a preamplifier if the T plus the excess noise, so DUT plus noise figure, is less than 30 dB, 35 depending on the frequency. In boxes of 26.5 gig and lower, if your device does not have greater than 30 dB gain, inclusive noise figure, you're going to need a preamplifier to get above the receivers. So it will require some external filters, and you'll probably need some filters also if you're doing receivers or mixers. Okay. So the calibration supports all of those. The calibration is not going to be number of these extra preamplifiers and so on being added. So consideration, like I mentioned, the preamplifier would be required, and if you take a look at the chain in that blue box, the IF inputs and so on, you'll see that we go through a fair amount of filter banks and so on for the noise receiver and the receivers themselves. So there's a fair amount of internal noise figure that we need to get above, and that's why putting internal filters and preamplifiers is going to solve our problems with that. Here's an example of both the PNA with option 28 and the PNA-X with option 29. You get that option 29 option is much cleaner. There's strenuous external devices required, but on the left side, the option 28 requires simplification and some filtering. So in both cases, you could still make the same accuracy of measurements, but it can be a little bit more complicated. All right. So using standard receivers, we are using you can see that D receiver there. We don't have an integrated noise receiver in this case, but we still do the vector and scalar techniques in both of these cases. If we compare the noise figure using standard receivers, we could see that gain plots are very similar. They actually, and take a look at the figure, and what we're showing you is the gain differences. So if we had a device that had a gain of 34 dB, we would noise figure with a certain amount of jitter on that brown line. If we drop the noise, the gain to 24 dB, we see that the purple line has a lot more jitter. And the reason for that is because we're now hitting the noise, the noise figure, or the figure of the receiver, now hiding the noise figure of the device we're trying to measure. Effectively, adding a preamplifier will pull the noise out of the noise floor of the receiver. Smoothing does help. By adding smoothing, we get a very representation of what the average noise is. That can help us to make some really decent, very accurate noise figure measurements in the where noise figure is lower than the effective noise figure at the front end of the network analyzer. What happens here is if we look at a high gain DUT, you'll see that there's two lines on top of each other. There's a pink line and an orange line right behind it. And the difference is that the pink line is the measurement of noise figure of a device with reasonable gain, and the orange line is a noise figure measurement with gain superior. See that in the C here. Unfortunately, I wish that was a different color, but we could see that the orange line has a lot less jitter on it and a lot smoother noise figure response. So the gain your device has, the low jitter is going to be in any measurement. And this applies also to Y-factor method, where you might have to add an external preamp to reduce the total jitter in the measurement. So again, comparing standard and low noise receivers. In our network analyzer, you probably saw in the diagram that you can actually pick the gains that you want, low, medium, or high. Depending on the device that you measure, you would increase the gain in the network analyzer to get a little less jitter in your measurement. Excuse me. So for adding a preamplifier to your noise calibration and measurement would be exactly like you see here. So we have the tuner again on the left-hand side to do vector noise figure. But in the past, within the links of the we'll have a preamplifier and some filtering. So it's actually, if you have the PNA-X, those are there. If you have the PNA with option 217 or 417, then those links are there available to you, so you can add some preamplification in line with the receiver. Okay. So another technique that we can use to increase or effectively reduce the noise figure of the front end of the network analyzer is by reducing its loss. And you can see on the front panel there are links. And those links, if I back up one slide, you'll see that those links allow you, those little black dots to the right where the beaver is, those are the links where you can effectively reverse the coupler, use the low loss path through to straight into the B receiver and the high loss path for the source part, so that you can actually decrease the noise front end noise figure of the network analyzer by 50 dB, flipping those and improving your noise figure capability. Here, if your gain of your device does not meet greater than 45 dependent frequency of the analyzer, by reducing those flipping links, we can actually give us a little bit more margin. We also have to consider for high gain setups, like the total power going into the receivers. We certainly don't want to compress or damage the B receivers. The S22 power also matters. So if we have an amplifier, like in this case here, but we effectively reduce the total power being transmitted back into the device at the S22, if a lot of noise on that S2 measurement, it will show up as noise ripple in the S21 measurement. So if the gain measurement has ripple in it, the noise figure will also have some ripple in it. Okay, so you got to be very careful in making sure that the total going to the device at the port to measure the S22 is good enough so that we don't have too much noise in that measurement. Averaging is going to help with the trace noise and making those parameter measurements. Noise is also available on converters. So same technique of vector and scalar for both 29 and 28 are available to make those S parameters on receivers, down converters and up converters. Okay, so instead of S21, we'll be using SC21. If it also works to have a receiver, it will also work with embedded LO, and we'll show that in a second. So we'll go to mixture measurements. You're going to get 3 tabs more in your setup, noise figure setup. These are the frequency setup for your mixers, the mixer power that you want delivered, and so a little bit of the mixer setup as to what ports you're going to be connecting your local oscillator to, etc. Embedded LO also very critical. So if you have a device that's a receiver, but it has its own LO, and we don't have access to its 10 megahertz reference, or we're not going to be delivering the local oscillator to your device, the phase component of both the receiver and the PNA are going to be uncorrelated. So what happens is that you're going to get a lot of jittery measurements going on. So doing embedded LO, the PNA actually determines what is the LO of your device by full subtraction math, and be able to set its input and output frequencies to match the LO of your converter. That way, you get a lot flatter gains and noise figure measurements across frequency. Also, a very big thing important, increasing averaging. You're going to reduce the jitter, provides a benefit of the average noise power, and overall slows down the measurement time, but by increasing your accuracy, sometimes that's very important, more important than time. So measuring noise figure, you could see here what happens when we do averaging. So with no averaging, it takes 5 seconds to make this wideband sweep here from 1 gigahertz to 26. So as we increase the number of averaging, you can see that the jitter reduces substantially and the time increases. Another very important thing when making noise figure measurements that you should be very aware of, especially for those devices on-wafer or devices that are not closed, you're going to possibly have interferers, and those interferers could come from cell towers, other sources in the lab, and they could show up as spikes in measurements. So most of the time, those are ingressed energy from cell phone and so on. So you're aware of that. Noise parameters are also available where we can actually plot gamma opt over a small region, and that region is really only over the source pole region of the ECal when we're doing vector. If you wanted to do basically general purpose noise parameter solutions over the full Smith chart, then using Maury techniques would be the best way, and I'll do that in a second. There's an example of doing a small load pull on figure. Talk a little bit about accuracy limitations. So there are many sources of measurement uncertainty. Every measurement technique that everybody uses is going to have its share of sources of uncertainty. And there's a whole list there. You know, instrument uncertainty is important, ER uncertainty, so how accurate is the X-noise ratio calibrated on those noise sources. Jitter, S parameter uncertainty, no parameter effects, so the figure versus a source match, mismatch errors, and the large source of errors are typically mismatch errors. And if you get the Y factor method, we have a source that has a impedance, the river that has a impedance. So during calibration, we're going to have a mismatch error, a little bit of the noise parameter effect there too. And so during measurement, there's going to be a mismatch between the noise source and the DUT, and also a mismatch between DUT and the noise receiver. So all of those in the Y factor are uncompensated for. They are unknown. They're corrected for. You have to live with them, and they usually, like I determined, the largest error term. You look at the cold source uncertainty method. With the VNA and the ECal, what we're actually doing is effectively removing all of the matches in the system And when we do the noise receiver calibration, there's a mismatch error there. However, since we have a network analyzer, we actually measure the impedance of that noise source during the noise receiver calibration, and we know what the mismatch of that noise source is, or the match of that noise source is. So we do the measurements. We no longer have any noise source at the input, the UT, basically the VA system that's fully calibrated. The mismatch error really is going to come into play. The vector is the mismatch on the output, but that mismatch is very well known. So we can actually calibrate and correct for it. So one of the largest errors now in the network analyzer are things like drift, jitter, power error, etc. For the Y-factor method, in case we would have no interaction between the source and the DUT, but the real world, we have this reflection that occurs between the two. When we take a look at noise parameters, we're trying to find out what the F-min and the gamma opt is, and PNA can only do a small portion of that with the vector cal, but we'll understand that the impedance affects where the noise, what the noise figure measurement would be because of these noise circles. Okay. So when we look at noise parameters, again, just to reiterate here, that gamma opt in that layer, and resistance, figure resistance, and the F-min are all dependent on impedance to the device. Okay. Again, just to reiterate, when with the network analyzer, we can actually characterize the impedance and correct for it. So it's a vector-corrected noise figure that we do. The noise figure analyzer and the Y-factor, it's a 50 ohm per system. Compare them. Noise directly to DUT and Y-factor is with a good source match, but if you now add cables and AT systems, then you can reduce that match and thus reduce your measurement accuracy. Cold source VNA, with source correction, we got a poor source match, but excellent for ATE and for longer cables because we can fully characterize the S parameter of those and remove the effect and also S parameter effect of the system when measuring the device. So we have a noise figure uncertainty calculator that's available, included with the noise source and power meter based calibrations. It includes a vector and scalar calibration, reports the uncertainty of the measurements that you're making. Okay. Also available at .com noise figure calculator. For example, I've got just a few more minutes here. Noise figure uncertainty, you can see stack. So in our case here, the network analyzer, you can see the total uncertainty for Y-factor measurements or a noise figure measurement of 3 dB. We have an uncertainty of about 0.2 dB. If we then add noise source directly at the DUT input for Y-factor, we're at about half a dB uncertainty. And then if we add switches or an ATE solution, it's good at another 3/4 of dB or so on. So the errors will all stack up, and this is an example of that. So if we broke that down into the uncertainty, we could see that the majority of errors in an ATE system is going to be due to imperfect 50 ohm source matches when we're looking at the Y-factor method in green there. For on-wafer. So on-wafer, there's a lot of error due to the fact that the Y-factor method cannot be done right on wafer. It has to be done extended away through probe and cabling. So the error gets larger. However, with the network analyzer, the PNA-X, we can reduce that error and keep a much tighter uncertainty due to the fact that we do calibrations right at the wafer plane and also extend using Okay, so again, due to perfect system, you could see that the largest error is always mismatch in terms of Y-factor. So look at this, the mismatch actually shows up as a ripple our frequency noise figure measurement. The PNA-X is a nice blue line, and you can factor the high ENR noise source, that large ripple across the measurement. Here, when we use a low ENR noise source, the difference between high ENR and a low ENR noise source is the fact that we've added a CB pad to the of it, reducing the excess noise ratio, but improving the match. All the techniques in terms of near PNA, and then for noise sources, we could see that effectively the PNA has a much less ripply calibrating process. Couple slides. We can extend the PNA noise figure measurements out to noise parameters, and a partner that we use is called Maury Microwave. So they have all their software and their tuners in order to do full min, gamma, op types of measurements using the full Smith chart and being able to actually measure noise factor, noise parameters over the full device range very quickly. So to get Maury, go see their website. They integrate systems outside of our network analyzers in order to make these high frequency and very accurate noise figure measurements. To summarize, Y-factor method offers really reasonable, easy setup to make DOT noise figure measurements. The source-directed cold source technique offers, the best accuracy in all cases, works well in fixtured on-wafer and AT environments, and is faster than the noise figure analyzer in most of its cases. So, I'd like to thank you for listening, and I hope that this has given you some information in terms of what it would be the best technique for you to make noise figure measurements in your near future.
Thanks, Jean-Marc, and thanks everyone for participation. This webinar has been recorded and will be available on CMC's website. I have a couple of minutes for a few questions. If you have any questions to ask Jean-Marc, please press *6 to unmute and ask your question. Thanks. Sorry, *7 to unmute and pose your question. Anything on Mark, there are some questions on the chat box.
See that there's a question here. Can we measure mixer noise with the PNA-X? So if you're talking about noise figure, we can measure noise figure with a mixer. That's NFX technique that I showed you earlier in one of the slides, is that we do have a measurement class available to make noise figure measurements over receiver, an up converter, or down converter. If you're talking about mixer noise as in noise power by itself with noise figure, that technique is more of a receiver technique, and that may be able to do. You might be able to do that with our new spectrum analyzer mode available in the PNA-X, but that still might be reserved to higher deck range spectrum analyzer mode. But in both cases, that is correct. We can make those noise measurements with receivers.
The other one was the highest frequency for noise figure measurement with PNA-X.
So the highest frequency we can go with noise figure measurements with the PNA-X is 67 gigahertz using the measurement receivers and 50 gigahertz using the noise receivers. So a little bit of discontinuity there, but those are the frequencies for in the box. So there's another question here. How was the smoothing performed? Smoothing is a norm, an integrated feature that's always been in the network analyzer. So you select what aperture you want. So basically say like 10% aperture, it would take 10% of points across the screen and give you an average number across that. So basically a rolling average across the screen, and it really removes a lot of the jitter.
As one other thing, can I set PNA-X IF bandwidth different from NF bandwidth?
Yes, both of those are different. So the noise figure bandwidth is basically only dedicated to the noise receiver, and then the IF bandwidth for the S parameters can be set separately, yes.
I guess that's in time, but it's 1 o'clock. And there are no other questions. Again, thanks everyone for participating. The webinar will be available online, and thank you, Jean-Marc, for presenting the webinar today.
Thank you very much.